Hi, in this presentation I'll talk about stochastic supersampling and especially jitter stochastic supersampling. This is a method for sampling average values out of the texture map to estimate the correct value that we want for the screen pixel. It's a kind of Monte Carlo integration. So you may have heard of Monte Carlo integration before. It's named after the gambling city of Monte Carlo. The idea is the following. You want to integrate some function. So if I say got the x-axis with x ranging from a to b, and I've got some function f here, and I want to take the integral from a to b of f. Well, one way to do this is we can express this as the average value of f on the interval ab times the length of the interval b minus a. And we can estimate by random samples the average value of f. Estimate the average value of f by choosing, say, k many values x in the interval AB at random, and then taking the average of the k values, f of k, f of x, I'm sorry, the k values, f of x. And the average for the expected value for that is, of course, the average of f. And if you have a good estimate of the average of f, you can multiply times b minus a and get a good estimate for the integral of f between between a and b. So this is can be a handy method to do integration when you don't have other techniques available. And you'll notice that if you remember Riemann integration worked by taking equally spaced values of x in the interval a, b, and then taking the average value of f of those equally spaced values. Monte Carlo integration is taking random values for f. So we'll talk about next how to apply that to texture mapping. So the situation with texture mapping is we would apply this kind of thing in a situation usually where the texture map has very high resolution. So let me draw a lot of pixels for the texture map. And the screen has relatively low resolution, so I'll just draw a small number of pixels for that. 3 by 3. And the idea here is that the screen, each point on the screen has a texture coordinate. So some point here has a texture coordinate, S0, T0, but every point on the screen, in fact, has a texture coordinate you can compute because we're computing these texture coordinates for positions on the screen by using averaging texture coordinates from the vertices of a triangle, using usually hyperbolic interpolation to get those. And so what we can do is we can supersample positions in the screen pixel. So here's our one screen pixel. I can pick k many values. So I'm going to pick maybe 9 many values. That's 3, 4, 5, 6, 7, 8, 9. And these values, k many positions in the pixel. So I've got k many subpixel locations. Inside that one pixel on the screen. And each subpixel location has a texture coordinates. And we come back here and we pick the corresponding positions in the texture map. And then we evaluate the texture map in the usual way, say using even bilinear interpolation or the nearest center if we wish. And we get 9 values out of the texture map in this case, or k values out of the texture map. and then we average those, and we use that as the value for the pixel. So k subpixel locations gives us k values from the texture map, and then you average those k values, to use for the screen pixel. So this is known as stochastic supersampling. So stochastic is another word for random, and supersampling means we're choosing more than one sample. Okay. So this can work okay, but it definitely has some problems. So one big problem is that it can have a lot of noise. Unless k is large. So when I say large, I mean maybe 50 or 100 or something like that, which is a pretty big value. And the point is that we've chosen these positions at random in the subpixel, but if you just choose positions at random, they're not going to be equally spaced. You're going to expect them to be some clumpiness. So here I drew them sort of clumped up into the upper left-hand corner of the pixel. So the samples out of the texture map were also clumped up together. The whole pixel there, in principle, corresponds to some patch, more or less rectangular shape inside the texture map. And we really wanted to get the average of all those pixels and use that as the value for the screen pixel. And by sampling here, we're just sampling some of the pixels. And although the expected value of the average in the probabilistic sense of expected is the exactly correct value, we do have a pretty big variation or standard deviation in the values. And that's due in part to the fact that the values tend to clump up together. So we'd like to have other techniques that work when k is smaller than. Now I'd like to talk about jittered stochastic supersampling as a way to address this problem with the noisiness requiring a large number of samples to fix. So let me redraw, however, first the pixel from the previous board. So I had on the previous board a 3x3 array of screen pixels. Let me just enlarge this, take an enlarged view. Here's one single screen pixel is this square here. And last time I picked 9 samples at random, more or less at random. So these are 9 subpixel locations, and we then use the averages we use the average of the texture values for those, and this was what we did with stochastic supersampling. So the other idea I want to combine this with is what's known as jittered supersampling. This is non-stochastic jittered supersampling. So jitter just means, jitter means to sort of push around or something like that in the regular pattern. So for jittered supersampling, we would I'll again use 9 subpixel locations as my picture, but in general we might use k squared many subpixel locations. I'll draw 9. So, but we're on a regular grid, so we use k squared many subpixel locations on a regular grid inside a single pixel. So again, this is one single screen pixel. So we would take these subpixel locations, we would take their texture coordinates, we would look up the position of the texture map, get the color out of the texture map for that position, and then we would average those results together and use that as the value for the pixel. So this is very straightforward, the problem here is that we can definitely still have issues with aliasing. Aliasing can still be a big problem. And what I mean is a big problem over just not doing any supersampling, just using one subpixel location. It won't be nearly as bad usually as picking a single subpixel location. However, because the subpixel locations are arranged on a regular grid, that means you're picking up values, potentially picking up values from the texture map on a very regular grid, and therefore patterns in the texture image could alias or interfere and give you all sorts of strange patterns in the rendered image. So to fix that, we want to combine the stochastic process with the jittering. And so for this, we do what's known as jittered stochastic supersampling. So for jittered stochastic supersampling, what we do is we divide the pixel up. I'll use k equals 3 again in the picture. We divide the picture, the screen pixel. This is again one screen pixel. We divide the screen pixel into a k by k array of subpixels. And just like before, we used k by k array of subpixel locations. Now we take at random from each subpixel a location. Okay, so I've chosen somewhat randomly 9 many subpixel locations, each from one of the subpixels, but at a random position inside that subpixel. Now I do the same thing as before. We take these k-squared many subpixel locations, we go back to the texture map, we get the color out of the texture map that corresponds to that subpixel location, and we take the average of the results. So this is actually a rather nice middle ground. So there's much less noise than with non-jittered stochastic supersampling. And that's due to the fact that there's much less bunching up of the subpixel locations. There can still be some bunching up, so like there's 2 here that are very close together, but there's tends to be a lot less bunching up, and that translates into less noise, and thus fewer supersamples are needed. There is still some possibility of aliasing. Aliasing is still possible, but it's less likely. So it is reduced, right? There's less aliasing. The aliasing comes from the fact that although we're not on a regular grid like in jittered supersampling, we're still there's still some pattern, especially when you get much larger than 3 by 3. There's still some pattern to the way the subpixel locations are placed, and so that can lead to interference patterns with details inside the texture map. But nonetheless, it tends to be a much higher quality and a nice middle ground where you can get by with not so many supersample locations. For instance, a 4 by 4 or a 5 by 5 tends to give very high quality results, even in demanding situations. So you don't have to use that many supersamples to get good results with jittered stochastic supersampling. Now, as I mentioned, this is not built into OpenGL, so you can't just turn this on as a feature. You can, however, program it up in a fragment shader, and it's commonly used, however, not so much in texture mapping, but more for techniques in ray tracing and so on. But it still makes a lot of sense to talk about it with texture mapping. one advantage with texture mapping is that it works even for images where the screen resolution and texture map resolution aren't strictly speaking comparable. So it may not be possible to say, and in that kind of situation, you can't use MIP mapping. So for instance, if you have a texture map that's applied to surface viewed at a sharp angle, you might have high resolution going back and forth away from the viewer, and low resolution on the texture map going sideways. So the texture map and screen resolution don't compare in the sense of one of them being higher resolution than the other. They're higher resolution, let's say the screen is higher resolution in one direction, and the texture map is higher resolution in the other direction. But jittered stochastic supersampling is completely independent of those kind of considerations, and it works fine even in that kind of situation, whereas MIP mapping would not work well in that kind of situation. So that's everything for this presentation. Thank you very much.